All right, folks, today we are going to be talking about average atomic mass. We know that the mass on the periodic table is the weighted average of all of the elements' isotopic masses. So what that means is that an element has multiple isotopes. Those isotopes they have certain abundances in the world, and the mass that's on the periodic table reflects which of those isotopes is the most abundant, and that's how we sort of get that weighted average. So for example, lithium has two common isotopes, and it has a mass of 6.941 AMU. AMU stands for atomic mass units. So if lithium has two common isotopes, but it has a mass of 6.941, you can probably guess that the masses are lithium 6 as an isotope and lithium 7 as an isotope. Which is more abundant? Well, the mass is closer to 7, so I would say that lithium 7 is more abundant of these two lithium isotopes. Carbon has a mass of 12.01 AMU, and it has three common isotopes, carbon-12, carbon-13, and carbon-14. Which is the most abundant of those isotopes? If you said carbon-12, you would be correct. All right, so we can use that mass on the periodic table to get an idea of what the most abundant isotope is of any particular element. Now, scientists determine the relative abundance of these different isotopes using something called time of flight mass spectrometry. We're just going to look very briefly at what that looks like. So basically, we get this graph here. So this is what the time of flight mass spectrometry graph looks like. Basically, the larger the peak, the more of that isotope there is in any specific sample. So here we see one very large peak around 11 and then a smaller peak around 10 AMU. So if we make a guess at what that average atomic mass might be, it might be, 10.8, right? It's going to be close to 11, but that mass from the 10 isotope is going to bring it down a little bit. So now using that, let's see if we can determine the identity of this element just from this chart, just from these isotopes. If we look at the periodic table, the element that has a mass closest to somewhere between 10 and 11 is boron. Boron has a mass on the periodic table, boron has a mass on the periodic table of 10.812 AMU. So it seems like we have boron here. We have that big peak near 11 AMU and a smaller peak near 10. So we can use time of flight to look at the relative abundances of certain isotopes, and we can even determine the identity of different elements based on these charts. But we can also do calculations with average atomic mass. We can actually calculate that mass that's listed on the periodic table. So the mass of any particular isotope, so the mass of any of the isotopes, we can multiply that by the abundance of that isotope. And then if we add the results together, we can determine the mass, the average atomic mass of that element. So if we look at this example here, we're dealing with silver. We have two isotopes of silver here. We have 107, silver 107, and silver 109. Now, these are the mass numbers from those isotopes, 107 and 109, but if we're being very specific with how much protons and neutrons actually weigh, this would be what their actual isotopic mass is in atomic mass units. So we have 106.905, that's pretty close to 107, and we have 108.905, which again, pretty close to 109. So if we go through how to do this problem, all we do is we take this average, this isotopic mass, so 106.905 AMU, and we are going to multiply it by its abundance. But we can't just multiply it by this percent. Remember from math, anytime that we deal with percents, we have to turn them into decimals. So to turn this number into a decimal, you move the decimal 2 times to the left, or you divide by 100. right? So to go to a decimal, you divide by 100. Okay, so both of these, there we go. So we would take the 106.905 AMU, atomic mass units, times 0.50958. When you do that, you get 54.4766. That's all I'm going to keep for now. Then we're going to do the same thing with the other isotope. So we're going to take the 108.905 AMU. We're going to multiply by that abundance, but in decimal form, so 0.49042. We're going to multiply that out, and we get 53.4092. All right, now we take these two numbers and we add them together. What we should end up with is the average atomic mass that's listed on the periodic table. So if we take these numbers, 54.4766 plus 53.4092, we add them up and we get 107.8858 AMU. The mass of silver on the periodic table is 107.868. So we are very, very close to that average atomic mass there. I'm not going to, in these calculations, give you the exact mass that's listed on the periodic table, because then you could just copy down that answer. That's silly. No. When we do these calculations, these examples, I'll tweak the numbers just enough so that you actually have to do the work. But let's see, does this answer make sense? Well, if we are looking at the relative abundances, it's about 50-50. Right? We have 51% of the silver 107, we have 49% of the silver 109, so we are expecting an average atomic mass that's pretty close to 108. Now, I'd say this is. Now, in terms of rounding, we are only going to keep 2 decimal points. Right? On the periodic table, yours should be rounded to 2 decimal points, so 107.89 will be the actual answer. Let's do another example. A sample of silicon has the following isotopic abundances. Now, in this problem, I didn't give you the exact isotopic masses, so you should use these mass numbers for those isotopic masses. So again, we're going to take the mass numbers and multiply by the percent abundances, but we need to turn these abundances into decimals. So 1, 2, 1, 2, and 1, 2. All right, so let's multiply all this out. We've got 28 AMU, and we're multiplying that by 0.9221. Okay, I'm going to write out all the work, and then you can do the calculating yourself. So 29 AMU times 0.0470. Got to be careful with those zeros there. And then 30 AMU times 0.0309. Now, before I even do any calculating, you should be able to guess where approximately this average atomic mass is going to be. We see that we have a lot higher abundance of silicon-28, so we should be expecting our average atomic mass to be on the 28 side, not on the 30 side of these isotopes. It'll be over 28 because we do have some of that 29 and 30 isotope, okay? But it should be close to 28. So let's do this math here. All right, so we get those individual answers there, and then we add everything together. So 25.8188 plus 1.363 plus 0.927, and it gives you 28.1088, but I'm going to go ahead and round it to 28.11 atomic mass units, which again, we said it was going to be close to 28. And if we look at the periodic table, the mass of silicon is 28.0855. So again, we are right in that ballpark. One more example for you. I want you guys to go ahead and do this one on your own. So pause the video and then check back here for the answers. All right, welcome back. Go ahead and check your work with what I have here. You'll see that I did move all of these into decimal form. I multiplied them by the mass numbers listed on the left-hand side over here, and ultimately what I got as my answer was 55.91 atomic mass units, which makes sense. If we look, the iron 56 is the most abundant, so we're expecting an average atomic mass that's close to 56. We got 55.91, and if we look at the periodic table, the mass listed there is 55.845 AMU. So hopefully this has given you a good idea of how to calculate average atomic mass or how to interpret average atomic mass. Please work diligently on that worksheet. Make sure that you are paying close attention to those decimals and zeros, and email me with any questions.